So today I'm going to be doing the compound JF4 for my drawing. This is going to be I'm going to be drawing my lowest diagram piece today. Look at this. Okay, I'm going to start with my first piece. It's all about the art. It's all about the art in chemistry. Nobody appreciates the artist in chemistry. And to start this drawing off, we have to first start with the structure of the artist, of the art that is in front of us. Look at this. We have re. Here's the mirror. We need more space for this art. It's because it's going to be beautiful. Absolutely beautiful. You have to put G in the center. You know why? Because it's the least electronegative. See that? It's the least electronegative. So we need to put it there according to the rules and the paper. Okay. After we do this, we need to find out how many electrons are in this compound. And according to my calculations over here, it's 36 C's. Okay, we're going to subtract 8 from that easily. Alright, 8 electrons. 8 electrons. We are counting the electrons because outside 8 from that is go, and we're going to get 28 electrons. After that, we're just going to fill up all the airs for optimum depth into the art that I'm drawing and this piece. Every one of them gets 8. It is known that every single one of them gets 8. After doing that, we have 6, 6, 6, and 6. We have 6 multiplied by 4, which is 28. Correct? Correct. But there's one is 46 multiplied is 4 multiplied by wait a second 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 19 20 21 22 23 24 24. Why don't you tell me, Gaston? Come on, Gaston, what are you doing? 24. We have 24 right here easily. So we need to put on the other 2 right here. Put one right here and right here. See that? Now we have 24, 25, 26, 27, 28. We filled up, we used up all our electrons. That is my first piece, and I'm going to name it octahedral. Going after it's what do you call it? It's electron diagram. It's because it's actually an octahedra according to the electron domains. 1, 2, 3, 4, 5, 6. 6 electron domains equals octahedral. Moving on to the second, to my magnum opus, to my second piece, and that is going to be the molecular geometry piece. It's going to be beautiful. Let's do it. I'll be drawing it right here. Going to do the J in the center, just like always, and we'll put the R over there. 1 second. Et là, je peux en put it. One ray right there. You have to put them on opposite sides every time. Okay, it's very known. No, this one's actually going toward us. Going away, going toward us. It's beautiful, absolutely beautiful depth and shading in the picture, in the piece. Gets me every time. You get what I'm saying? Of course you do, Gaston. Of course you do. Okay, look. And we then that we put the two lone pairs right there on each opposite each other. You have to put them on the opposite each other. This is actually a 90-degree, actually a 90-degree bond angle in between them. Everyone knows this, okay? Everyone knows there's a 90-degree bond angle, and of course the bond arrows. The bond arrows is right there. Those are how those go. If you don't know, it's very known to do that. They have to be going away from the least electronegative thing here. And the least electronegative is the J. The J right there is the least electronegative. That's why it's in the center, and all of them are going away from it. If all of them are going on all different sides and then they're not going in the same direction, it's not going to be a polar. It's not going to be a polar molecule. It's not polar molecule because all of the polar arrows are going in different directions. They're not all going in one direction. So it's non-polar. It's clearly non-polar. Okay, and not to forget the S plus and the S minus, S minus, S minus, the S minus, and ZS minus. Oh, quick correction. The actual polars, the actual lone pairs don't get no polar arrows. I'm sure they don't. Okay, and there we go. That is my second piece and my magnum opus. Going to sign it. Magnificent. Let me see if I'm missing anything according to my list that Gaston made for me. Door Louis Taxa, croissant, pistachio. Dat er nog tegen. Dat we het overlap. Oh, steeds zo bond hybridization of the sensor aardschroon. It is clearly SP3 dichter. As you can see, it's right there. Why? Because there's 6 electron diagrams. As we said, 1, 2, 3, 4, 5, 6. So if that happens, we have 1, 2, 3. We have 1 and then 3 and then 2. 1 plus 3 plus 2, 6. Right, Gaston? Okay. That's what I'm saying, Gaston. So now, Gaston, play Lenose de Figaro. And that is the electron diagram for this for this molar compound. I mean, look, one goes away from you, one goes towards you. It is a square planar. Okay, it is a square planar. Clearly, one's up or one's down, goes away from you, goes towards you. Very easy, just like the diagram. The polar bonds, same direction. So it's going this way. I may be an artist, but I'm not no. But I am not. I repeat, I am not a what do you an engineer. Okay, so look, this is hard. I couldn't do anything. Look at it. There we go. Beautiful. Absolutely beautiful. Kind of. Look. It's done. Okay, there you go. There you go. One's going away from you, one's going towards you. That's those are the two lone pairs, and that's the last thing. Easy. Done. These are the what do you call it? These are the A's. That's the J, the big J. That's the lone pairs, and those are the perfectly matches. Perfect. Beautiful. There's nothing like it. Okay, non-polar sp3d2. I mentioned everything. And now let's end the video. That's all of it. That is all of it. Now, I'm going to sing my solo Gaston camera over here. Figaro, 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 Figaro. La finito.